This video is brought to you by ThePuzzlr.com. Here are the questions, answers, and explanations from the second ThePuzzlr contest. And stay tuned for a bonus AoPS gift card giveaway at the end. Here are the middle school questions from the contest. Number 1. What is the value of 4 plus 6 divided by 2/3? To solve this problem, we apply a technique called PEMDAS, which relates to order of operations. If you don't know what PEMDAS is, be sure to watch our video on it, as there are a lot of problems concerning that on the test. The first step of PEMDAS that we apply in this problem is division. Let's write the division part of this problem in parentheses. We get 4 plus 6 divided by 2/3. Whenever you're dividing by a fraction, it's the same thing as multiplying by its reciprocal, which is usually easier to calculate. So we can rewrite this as 4 plus 6 times 3 divided by 2. The 2 cancels out from the top and the bottom, and it gives us 9. This expression is equal to 9. So we rewrite this as 4 plus 9, which is equal to 13. Let's move on to problem number 2. Oliver has 12 coins, all of which are nickels and dimes. If the value of the nickels is equal to the value of the dimes, what is the total value of his 12 coins in cents? Let's say there are n nickels. Well, each nickel is worth 5 cents, so the total value of the nickels is 5n. The problem states that the value of the nickels is equal to the value of the dimes, so we know that the value of the dimes is also 5n. Since each dime is 2 times as valuable, we only need half as many dimes for it to be equal. So we have n divided by 2 dimes. Since there are only nickels and dimes, we can add these total n and 1/2 n to get the total number of coins. The problem also states that there are 12 coins, so we know that this number is equal to 12. Adding this left-hand side up, we get 3/2 n is equal to 12, or n is equal to 8 if we multiply both sides by 2/3. That means that there are 8 nickels, so the value of the nickels in cents is 40. We also know that the value of the dimes is the same, or 40. So the total value of the nickels and the dimes is 80 cents. So our answer is 80. Let's move on to problem number 3. Number 3. 12 painters paint 12 houses in 12 days. How many days would it take 10 painters to paint 10 houses? Let's use logic to solve this problem instead of any formulas. If 12 painters paint 12 houses in 12 days, then if we had 1/12 of the painters, or one painter, then we would only paint 1/12 of the houses. So that means one painter paints one house in 12 days. Well, the next logical step is to multiply the number of painters by 10, since we have 10 painters in the desired problem. If we multiply the number of painters by 10, then it makes sense that we have to do the same thing to the number of houses that we paint. But we get lucky in that this is exactly what we wanted, as we have 10 painters in the original problem and 10 houses, like in our result. And notice that the number of days never changes. So our answer is just 12 days. Let's move on to problem number 4. 2 sides of a right triangle measure 8 and 15 units. If the length of the hypotenuse is not equal to 17, the length can be expressed in simplest radical form as square root of k. What is k? So we have 2 possible options here. We have to note that the hypotenuse is always the longest side of a right triangle. So it cannot be 8 since 15 is longer than 8. But it could be 15, or it could be some other number that we don't know about. First, let's assume it's not 15. Well, that means the number is bigger than 15. Then our legs have to be 15. And our mystery number, let's call it C for now, is C. So applying the Pythagorean theorem, we can solve this problem. 8 squared plus 15 squared is equal to C squared. This is 64 plus 225 is equal to C squared. Or 289 is equal to C squared. And C is equal to 17. But the problem specifically tells us that the answer is not 17. So this is invalid. Then we have to consider the other scenario, where 15 is the longest side. So let's consider that scenario. In this case, we have to figure out what the third leg is, or the second leg is. So we know that one of the legs is 8. It doesn't matter which one we make 8. And the hypotenuse is 15. Let's let this leg equal b. So we know that 8 squared plus b squared is equal to 15 squared. 8 squared is equal to 64. And 15 squared is equal to 225. Subtracting 64 from both sides, we get b squared is equal to 161. 161 is not a perfect square, so we get b is equal to the square root of 161, which is equal to the square root of k as the problem tells us. So k is equal to 161. Our answer is 161 units. Let's move on to problem number 5. Number 5. If A pound B is defined as A times B and A $B is defined as A plus B, for how many ordered pairs of integers xy does x pound y equal x $y? So the first thing that we do is we rewrite both sides of these equations in terms of operations that we know. X pound y is just equal to x times y, as the original problem states. So we get x times y is equal to x $y, which is equal to x plus y. Now here, note that both numbers cannot be negative, as if both numbers are negative, the left side is going to be positive, and the right side is going to be negative, which means that won't be possible. A trivial solution that we note is 0, 0, as if both x and y equals 0, both sides of the equation will equal each other. Now let's assume that both of these numbers are not 0. Then we can rewrite this equation as xy minus y is equal to x. Let's factor out the y on the left-hand side. And we get y times x minus 1 is equal to x. Since both x and y are an integer, this means that the left-hand side, both these terms, or factors, are factors of the number x. So that means y is a factor of x. Now let's rewrite this equation another way. Instead of subtracting y from both sides, let's subtract x. Then we get xy minus x is equal to y. Once again, factoring out the x, we get x times y minus 1 is equal to y. Applying the same logic as before, we know that x is a factor of y. Now, if x is a factor of y and y is a factor of x, that is only possible if both x and y are equal to each other. So now we have another piece of important information, namely that x is equal to y. So now, using substitution, let's plug y back into the original question. 4x. So we get x squared, as y is now replaced with x. And on the right hand side, we get x plus x. So this is x squared is equal to 2x. Subtracting 2x from both sides, we get x squared minus 2x equals 0. And factoring this, we get x times x minus 2 as our solutions. This tells us that either x is equal to 0, which that's the solution that we already derived, or x is equal to 2. Then, applying this in this equation, we know that y is also equal to 2. So we found another point that satisfy these equations. So our two answers are 0, 0 and 2, 2. Let me write that right here. 0, 0 and 2, 2. Let's move on to problem number 6. Number 6. One square is inscribed in another as shown, such that the smaller square divides the larger square's sides into two segments of the ratio 1 to 2. Let the area of the inscribed square be A, and let the area of the region that is inside the large square but outside the inscribed square be B. What is 100 times the ratio A to B? So we know that this area is equal to B. So let me mark that on this painting, on this drawing. So we have that the area inside is equal to A. Okay. We also know that the area of the white triangles is equal to B because that's the area that's inside the larger square but not the smaller square. So the area of the larger square is equal to B plus A. Now, since we're concerned with ratios and not actually finding the area, we can assume any length, any number for this length. Let's assume this to be 1. Then, since there's a ratio of 1 to 2 between the shorter side to this longer side, we know that this is equal to 2. Similarly, we know that this is equal to 1. Since this is a square, this is a right angle. We can apply the Pythagorean theorem here to find this side. So this side is equal to 4 plus 1. And we square root that to get the square root of 5. So this side is equal to the square root of 5. Since the sides of the inner square are equal to the square root of 5, the area of that square is equal to 5. We also know that the area of the outer square with 3 centimeters or 3 units of length is 9 because 3 times 3 is equal to 9. Since the area of the larger square is B plus A and A is equal to 5, B must equal 4. So A is equal to 5 and B must equal 4. This satisfies all the conditions in this problem. So the ratio for A to B is 5 over 4. Multiplying this by 100, the 4 cancels out from the top and the bottom. We get that the answer is 125. Let's move on to problem number 7. How many more 5-digit palindromes are there than 3-digit palindromes? First, if you don't know what palindromes are, be sure to watch our video on it because it goes over the simplest applications of palindromes and how to calculate questions like these. So the first thing that we do is calculate the number of 5-digit palindromes. Let there be a 5-digit number like this. And let's assume the first digit to be A, the second digit to be B, and the third digit to be C. Well, since this number is a palindrome, the reverse of it has to be the same. So this digit also has to be B, and this digit also has to be A. Now, whenever you have two independent items, to find the total number of combinations, You just multiply the number of ways that you can have the first item and the number of ways that you can have the second item. So the number of choices that we have for A are 1 through 9. So we have 9 choices for A. B can be anywhere from 0 to 9. So we have 10 choices for B. Now for C, once again, it could be anywhere from 0 to 9. So we have 9 times 10 times 10 choices. B and A, since we already fixed them at the beginning, are already done. So now we have 900 total 5-digit palindromes. Let's now do the same thing for 3-digit palindromes. Let's assume the first digit to be A, the second digit to be B, and since it's a palindrome, the third digit has to be A once again. We have 9 choices for A, just like last time. And we have 10 choices for B, from 0 to 9. This gives us 90 total palindromes that are 3 digits. Since we have to find their positive difference, we do 900 minus 90 and get our answer of 810. Let's move on to problem number 8. Number 8. Suppose there are 3 people, Zack, Yolanda, and Xavier, each of whom make these claims. Zack says Yolanda is telling the truth. Yolanda says Zack is not guilty. Xavier says Zack is guilty. Given that only one of them is telling the truth, can you determine who is guilty? This problem is a knights and knaves problem, where a set of people are telling the truth and the other people are lying. To solve this problem, we apply a series of techniques that are clearly explained in our knights and knaves video, which you can watch right now. The answer to this problem is that Zack is the one who is guilty. Let's move on to number 9. Number 9. What is the smallest positive value of x where x does not equal 1, such that the last 4 digits of 2020 times x are 2020? We apply a bit of logic to solve this problem. We know that our number must end in some sort of zeros plus 1 so that the last 4 digits are equal to 2020. Let's assume that our number is a 3-digit number. Well, we have to have some A and multiplying that by a 100 to account for the fact that it's the hundreds digit. Plus, we can assume that the B is going to equal 0, since that's the only way that the last 4 digits would equal 2020. So we get 100A plus C times 2020. This gives us 2020 times 100, which is just adding 2 zeros to the end, plus, so multiply that by A, plus 2020 C. Now here, these 2 digits don't matter because we're only looking for the last 4 digits of the number. We want the C to equal 1 so that these last 4 digits are 2020. So let's let the C equal 1. Now we want this number to just go away. And by that, I mean that the last 4 digits are equal to 0, 0, 0. For the last 4 digits to equal 0, 0, 0, we can have A equal to 5. Thus, our number is equal to 501. That is the smallest positive value of x, such that the last 4 digits of 2020 times x are equal to 2020. Let's move on to problem number 10. I have 21 coins, all of which are nickels and dimes. If the total value of the nickels is the same as the total value of the dimes, what is the total value of my coins in cents? As you have probably noticed, we had a very similar problem to this earlier, and that's why we're going to leave this problem to the viewers to solve on their own. But we will give you the answer, so pause now if you want to solve this on your own. The correct answer is 140 cents, because there are 7 dimes and 14 nickels. Let's move on to problem number 11. How many 2-digit numbers with x in the tens column and y in the unit column have the property x minus 3 squared plus y minus 2 squared is equal to 0. Since x minus 3 squared is a perfect square, and y minus 2 is a perfect square, they both must be positive. In fact, any squared number is positive. That means that the least value of this function, or this equation, is 0, because the least value of this is 0 and the least value of this is 0. And additionally, the only time this is going to equal 0 is when both of these terms are equal to 0. So we can just solve these separately. For x minus 3 squared to equal 0, x minus 3 must equal 0. So x is equal to 3. Similarly, for y minus 2 squared to equal 0, y minus 2 must equal 0. So y is equal to 2. There's no other way to solve this problem. So our 3-digit number, or our 2-digit numbers that satisfy this problem are 32. So there's one 2-digit number that satisfies this problem. So our answer is 1. Let's move on to problem number 2. In how many ways can I arrange 5 keys around a keychain? Arrangements are considered the same if they can be flipped or rotated to be made the same. To solve this problem, we have to realize that there are a lot of arrangements that are same. Each arrangement of 5 keys can be rotated in exactly 5 ways, or 4 ways plus the one way that it has been set in. And each of these arrangements can be flipped to make another arrangement. So, to arrange 5 keys in a row without any regard to putting it around a keychain, there's 5 factorial ways. If you don't know this, then be sure to watch your video on factorials. It goes over this type of math. Since each arrangement can be flipped, we divide by 2 to account for that, since arrangements are considered the same if they can be flipped or rotated. And since we can rotate each arrangement in 5 ways, we also divide by 5. 5 factorial is equal to 120. Dividing 120 by 10, we get that there's 12 possible ways for us to arrange 5 keys around a keychain. Let's move on to problem number 13. Number 13. In the year 2013, the last digit is the same as the sum of the other 3 digits. How many years ago was this last the case? Okay, to solve this problem, let's first maximize the thousandths digit. Since it must be before 2013, to maximize the thousandths digit, it must be 2. Now we're left with 3 more places. The second digit must be 0 because if it's greater than 0, then it would be greater than the number 2013, which is not allowed. Now, the third digit can't be greater than 1 because if it is greater than 1, then it would be greater than the year 2013, which is once again not allowed. So let's assume that it's 1. But now the fourth digit has to be 3, as it has to be the sum of the other 3 digits. This is 2013, which is given in the problem, so we have to find a year before this. So let's change 1 to 0 this time. And now the fourth digit has to be the sum of other 3 digits, so it has to be 2. This is a valid case, and it is the latest year before 2013 where the last digit is the same as the sum of the other 3 digits. How many years ago was this last the case? We can subtract 2002 from 2013 to get our answer of 11 years. Let's move on to problem number 14. Number 14. How many ways are there to arrange Anna, Beth, Connor, Dean, and Ella in a row if Connor and Dean insist on sitting together? First of all, to solve this problem, you need to know about factorials and their applications in solving a problem like this. If you don't know about that, be sure to watch our video on factorials before you take the puzzler contest. We notice that there are 5 people here, but 2 of them insist on sitting together. So what we do is we act like this is one person. Connor and Dean are just one person. And let's assume that there are 4 spots to arrange them in a row. So Connor and Dean, whichever spot we pick for them, there would actually be 2 chairs for them to sit there. So, to arrange 4 people in a row, like mentioned in the factorials video, there's 4 factorials way, or 4 times 3 times 2 times 1, which is 24. But notice that when we're packaging Connor and Dean together, or making them into one group, we could either put Connor first and then Dean, or Dean first and then Connor. So we have to account for that and multiply by 2. So our final answer is 48. There are 48 ways to arrange 6 people in a row where 2 of them want to sit together. Let's move on to problem number 15. The biggest possible natural number n for which n to the power of 200 is less than 5 to the power of 300 holds true is. First of all, a natural number is a number that is an integer and positive. For example, our counting numbers like 1, 2, 3, 4, and so on. To solve this problem, we take the 200th root of both sides. Now notice that when we're taking the nth root of a number, that's actually the same as taking that number to the power of 1 over n. So, in this problem, we have n to the power of 200. Let's take it to the 200th power, so multiply by 1 over 200. And whatever we do to one side of the question, we have to do to the other side. So we get 5 times 300 to the 200th root. So here the 200s cancel out. So we're left with n is less than 5 to the power of 3 divided by 2. Now we just have to calculate what 5 to the power of 3 divided by 2 is, approximately, as n is an integer, not a rational number, or irrational number. Let's first calculate 5 to the power of 3, which is 125. Now we need to calculate the square root of 125, as something to the power of 1/2 is equal to the square root. Since 125 is greater than 121, which is the square of 11, we know that this number is between 11 and, so this number is between 11 and 12. Well, it says that n is less than this number. And since we're looking for the biggest possible natural number n, our answer is 11. Let's move on to problem number 16. Number 16. An equilateral triangle and a regular hexagon have equal perimeters. If the area of the triangle is 4, what is the area of the hexagon? So notice that if the side length of the triangle is equal to x, then the side length of the hexagon is equal to x divided by 2. The area of the triangle x is x squared root 3 over 4, as that's the formula for finding the area of an equilateral triangle. The area of the hexagon, where each side is x over 2 as your perimeter is the same, is x over 2 squared root 3 over 4 times 6, as there's 6 triangles. So here, simplifying stuff, we get x squared root 3 over 16, so over 8. So we get something like this when we simplify this part. So if you notice that this part is equal to 4, and if we multiply this by 3/2, we would get this expression right here. So we need to multiply 4 by 3/2 to find the area of this. And this would give us 6. So our answer is 6. Number 17. If you add the first n positive integers, you obtain a 3-digit number with all 3 digits being the same. How big is the sum of the digits of n? To find the sum of the first n positive integers, we apply a very well-known formula, n times n plus 1 divided by 2. We know this is equal to a 3-digit number where all 3 digits are the same. So let's let that 1 digit equal a. So our 3-digit number is a. Let's multiply both sides by 2 to get 2 times a. Now writing a as place value instead of this weird expression, we get n times n plus 1 is equal to 2 times 101 times a. I'm sorry, times 111 times a. So if you don't understand this, pause the video and try to come up with this on your own. So now we know that n times n plus 1 is equal to this expression. So let's try to find the prime factorization of this, or as far as we can get. 2 times, let's factor 111, 3 times 37 times a. So notice that this is 2 numbers that differ each other by 1. So if there was some way, since 37 is so big, that we could either get 38 or 36, our problem would be solved. 2 times 3 is equal to 6. 6 times a we want it to give us either 36 or 38. And luckily, if we let a equal 6, we get that 6 times 6 is equal to 36. So n would equal 36, or n would equal 36 when a is equal to 6. The problem states how big is the sum of the digits of n. So adding up 3 plus 6, we get our answer of 9. Problem number 18. On a standard 8x8 chessboard, only the knight sits on the board at the bottom left corner, A1. Recall that a knight moves 2 squares vertically and 1 horizontally, or vice versa. Dimitri will move his knight so it visits every square on the checkerboard exactly once. The probability that the knight will end at the upper right corner, H8, is best described as. For this logic-based problem, we're just going to give you the answer and ask you to solve it on your own with a reason. Be sure to comment down below with the explanation if you think you have it. The answer is impossible, but can you prove why? Let's move on to problem number 19. 10 different numbers are written down. Each number, which is equal to the product of the other 9 numbers, can then be underlined. What is the maximum amount of numbers that can be underlined? Let P be the product of the numbers in the set. And let's say there are 3 numbers, A, B, and C, which are each equal to the product of the remaining 9. So in this case, the numbers that we would underline are A, B, and C. Then we can say that P divided by A is equal to A, since the product of the other 9 numbers, excluding A, should be A, which gives us that the product of all the numbers is equal to A squared. In a similar way, we can prove this for B and C. So that means that A squared is equal to B squared is equal to C squared. From this it follows, just looking at this first equation, A is equal to B or negative B, and C must be one of those, making the set of numbers very similar. So now we need to construct a set of 10 numbers so that only 2 numbers are underlined. Let's say a is greater than 0 and negative a be the two underlying numbers. Then we can let our numbers be a, negative a, b, c, d, e, f, g, h, and I. And then the product b, c, d, e, f, g, h, I equals negative 1. So the maximum amount of numbers that we can underline are 2. This is because finding or underlining 3 numbers can be proved by contradiction. Number 20. Find the value of this expression. So the first thing that we notice is that the things in the parentheses are arithmetic sequences. If you don't know what arithmetic sequences are, be sure to watch our videos on them that go over everything that you need to know about them for the test and how to find the sum of series like these. Applying the formulas that are present in that video for the sequence on the top, we get that the sum of the first term plus the last term, let's calculate that, gives us 300,000. So now we divide this by 2 as per the formula. And then we multiply the total by the total number of elements. Notice that each of the terms iterates by 1 at the end. Or iterates by 2 at the end. So that means that these are just the number of odd numbers that are from 1 to 99999. That gives us 50,000 numbers. Now we multiply this by the 10 that's present in the numerator. And we now solve the denominator. So there's a 3 already there. And solving this arithmetic sequence in a similar way, we get that there's 100,000 as the sum. And we divide this by 2. Now we multiply the total number of elements, and if you notice that there are the same number of elements on the top as the bottom, we get 50,000. So notice that most of the stuff cancels out. The 50,000 cancels out from the top and the bottom. So does the 2. And so do these 5 zeros. And so does this 3. We're just left with this 10. So our answer is just simply 10. Let's move on to problem number 21. Number 21. How many digits are there in 2 to the power of 100? Note that this was a no calculator test, so there's no calculators allowed. The first keen observation that we make is that 2 to the power of 10. 2 to the power of 10 is equal to 1024. Notice how close this number is to 1000. In fact, it's so close that multiplying 10 of these numbers wouldn't change anything. So we have 2 to the power of 10 to the power of 10. Using the rules of exponents, we know this is the same as the question that we have to find, 2 to the power of 100. So we rewrite this as 1024 to the power of 10. And since we only have to find the number of digits, and this number is so close to 1000, we can just make it 1000 to the power of 10. Now this is equal to 10 to the power of 30. Pause your video right now if you don't understand why. And 10 to the 30 is the number 1 followed by 30 zeros. This gives us 30 zeros plus 1, so 31 digits. Let's move on to problem number 22. Number 22. If one of the numbers 1, 2, 3, all the way to n minus 1 and then n is crossed out, the average of the remaining numbers is 4.75. Which number was crossed out? For this problem, we give the answer to the viewer. It is B. And we will leave it to you to find why. Let's move on to problem number 23. Number 23. If the whole number age of a father is multiplied by the whole number age of a son, one obtains 2015. Both are born in the 19th century. How big is the age gap between father and son? The first thing that we do is find the factors of 2015. We can do this by finding the prime factorization of 2015, which is 5 times 13 times 31, where the exponent of each prime factor is 1. Now, using our how to find the number of factors of any number video, we know that this number has 2 times 2 times 2, or 8 factors. Here are the 8 factors: 1, 5, 13, 31, 65, 155, 403, and 2015. Now we use the statement that both are born in the 19th century. That means at max, they're 115 years old, and at minimum, they're at least 15 years old. So that means it can't be 2015, 403, 155, 1, 5, or 13. So the only ages that are left are 31 and 65. Since the father is older than the son, we know that the father is 65 and the son is 31. We can find their age difference by subtracting 31 from 65 to get 34 years. So our answer is 34. Let's move on to problem number 24. Problem number 24. There are 1,000 lockers in a gigantic room. 1,000 students are in the room. The first student goes down the line of lockers and opens all of them, starting with locker number 1. The second student goes down the line and closes every second locker, starting with locker number 2. The third student goes down the line and changes the state of every third locker, starting with locker number 3. If it is open, it gets closed, and if it's closed, it gets opened. The fourth student changes the state of every fourth locker, and so on, until all 1,000 students have taken a turn changing the state of the lockers. How many lockers will there be open in total at the end of this crazy endeavor? Let's look at a locker K. How many times does this get opened or closed? If this locker has an odd number of factors, then this locker will be open at the end. And if there are even number of factors, the locker will remain closed. If you don't get why this is true, pause the video and try to make sense of this. In this problem, we have to determine what numbers have an odd number of factors. Usually, numbers have one corresponding factor for every unique factor that they have. For example, let's look at the number 18. They have 1 as a factor, and thus there's a respective corresponding factor for 1, which is 18, since 1 times 18 is equal to 18. And this is always going to be true for most of the factors. So for 2, we have 9, for 3, we have 6, and so on. But they do repeat after that, so that doesn't count. You'll notice that they always multiply to 18, so there's always an even number of factors. The only time there would be an odd number of factors is when these two numbers, so for a factor pair, the numbers are the same. For example, the number 9. The number 9 has 1 and 9, which is equal to 9. And then 3 times 3. So even though here we have two factor pairs, since one of the factor pairs has duplicate numbers, it has an odd number of factors. But what does this mean? Having a duplicate pair means that the number is a perfect square. So the only time that a number will stay open is if it's a perfect square. From 1 to 1,000, there are exactly 31 perfect squares, as 961 is the biggest perfect square before going over 1,000. So at the end of this endeavor, there will be 31 total lockers that are open. Number 25. The positive whole number n has exactly 6 different positive factors, including 1 and n. The product of 5 of these factors is 648. Which of these numbers is a 6th factor of n? So So you have to know how to find the number of factors of a number to solve this problem. If you don't know that, be sure to watch your video on it. Now, 648 is divisible by both 2 and 3. So that means that in the prime factorization of n, there's a 2 present and there's a 3 present. Now, using what you learned in the factors video that we have on our channel, either the prime factorization of n is 2 squared times 3, as that gives us 6 factors, or it's 2 times 3 squared, as that also gives us 6 factors. Let's try each of these examples. Here, I've written the possible factors that we have of each prime factorization. So 2 squared times 3 is equal to 12. And the factors of 12 are 1, 2, 3, 4, 6, and 12. None of them, no 5 of them multiplied together give us 648. So that is invalid. Let's look at 2 times 3 squared. That gives us 18. The factors of 18 are 1, 2, 3, 6, 12, and 18. Well, 1 times 2 times 3 times 6 times 18 give us 648. So the sixth factor is 12. Let's move on to problem number 26. Problem number 26. A peculiar 100-pound watermelon is 80% water. Adam bought it from his local supermarket. He accidentally left it outside, where it dried up to become only 60% water. What is the new weight of this new dried up watermelon in pounds? This problem is very much like the Martian potato paradox, and if you don't know what that is, be sure to watch our video on it. Using a principle stated in that video, we know that this watermelon now actually has to be 50 pounds, so our answer is 50. If this doesn't make sense to you, be sure to watch our Martian potato paradox video for a complete explanation to this. Let's move on to problem number 27. Number 27. Dr. Smith gave Joseph 10 vitamins with instructions to take 1 or 2 each day until he runs out of vitamins. For example, Joseph could take a vitamin a day for 10 days, or he could take 2 the first day and 1 a day for the next 8 days. A third way is to take 1 vitamin a day for 8 days and 2 on the 9th day. Including the 3 examples given, in how many different ways can Joseph take the 10 vitamins? There are many tedious ways to do this problem involving casework. One such way is to count the number of times that Joseph decides to take 2 vitamins and find the total number of combinations for each. But ThePuzzlr aspires to bring you interesting puzzles that are not just boring computation but rather have a concept behind it. So the concept that can be applied to this problem is recursion. Let me explain further. If Joseph had only 3 vitamins, he could have either taken 2 vitamins or 1 vitamin on the last day. If he had taken 2 vitamins on the last day, then he has 1 vitamin left over. If he had taken 1 vitamin on the last day, then he has 2 vitamins left over. Therefore, the number of ways that 3 vitamins can be taken is equal to the number of ways that 1 vitamin can be taken, which is 1 way, plus the number of ways that 2 vitamins can be taken, which is 2 ways. We can generalize this for n number of vitamins. The number of ways that n vitamins can be taken is equal to the number of ways that n minus 1 vitamins can be taken plus the number of ways that n minus 2 vitamins can be taken. Since we already know how many ways we can take 1 or 2 vitamins, we can create a chart. This is just like the Fibonacci sequence, if you've ever heard of that before. Applying the Fibonacci sequence here, we need to find the 10th term, where the first term is 1 and the second term is 2. Let's find the 10th term this way. So we keep on adding the previous 2 terms to find the next term. We have 5, 8, 13, 21, 34, 55, and 89. Since there are 10 vitamins, we're looking for the 10th term in the series. So there are 89 different ways for Joseph to take the 10 vitamins. Let's move on to problem number 28. Gerard chooses two numbers A and B from the set 1, 2, 3, and all the way to 26. The product A times B of these two numbers is equal to the sum of the remaining 24 numbers from this set. How big is the absolute value of A minus B? The answer to this problem is 6. We now leave it to the viewer to find which two numbers A and B are. And now, time for the giveaway to win an AoPS gift card. Here's how you can enter this giveaway. To enter the giveaway, you have to do two things. Subscribe to our channel if you have not done so yet, and number 2, comment down below with your favorite question from this contest. Winners will be announced at ThePuzzlr.com/giveaway winners. Check out ThePuzzlr.com for more content, and be sure to subscribe to our channel if you enjoyed this video.